In this video, we are going to discuss the integrations of a fractional function, which is made up of a denominator containing an irreducible quadratic factor and a repeated linear factor. We first write the integrations of the integrand in the forms of r, where r is expressed in the forms of 2x plus 4 divided by the denominator function, which is comprised of an irreducible quadratic factor and an repeated linear factors x minus 1. The rules of partial fractions requires the functions r be expressed as the sum of three partial fraction terms. The first partial fraction terms contains the irreducible quadratic factors. Second and the third terms comprise of the linear factor x minus 1 and x minus 1 repeated twice. Since the linear factor is repeated twice, the decompositions of r into the linear factors should also contain two such terms. One term is the linear factor raised to the power of 1 and the second raised to the power of 2. The numerator for the irreducible quadratic factors has to be a linear factors of the form ax plus b. The second and third partial fractions, which comprise of an linear factor x minus 1, should contain a constant c and another constant d. Therefore, the integrations of the fractional functions r could then be decomposed into four different integrations of the following form. The integrations of the original fractional functions can then be obtained by summing up the individual integrations a, b, c, d terms independently. Proceed with our calculation. We first perform integration for the term involving a. The integration involving the a term is quite straightforward. This could be done by simply substitute x squared plus 1 to be y, so that the differential of dy is written as 2x dx. The numerator x dx is replaced by this term, which is dy over 2. The term x squared plus 1 is replaced by y, and you arrive at the log of y plus a constant. Expressing y in terms of x gives you this expression, which is the result of the integration involving the a term. The integrations of the b term could be obtained by recalling the fact that the differentiations of the function arctangent give you x squared plus 1. Therefore, the integrations of 1 plus x squared is simply the arctangent. So the integration of the b term is b times arctangent x plus n constant. Now we will discuss the integration of the c term, which is simply log of x minus 1 plus n constant. The integrations involving the d term could be performed by substituting y as x minus 1, so that this integration is straightforwardly reduced to dy over y squared, which results in this, and consequentially minus dy to the power of minus 1 plus a constant, which translates into minus d over x plus 1 plus a constant. We can now fill up all the result of the integrations term by term. The integration of the a term is log of x squared plus 1. Integrations involving b terms is b of arctangent of x. Integrations involving the c term give you log of x minus 1, while the integrations of the d terms is minus 1 over x. And don't forget, we have an arbitrary constant c at the back. So up to this point, we have successfully performed the integrations of the fractional function r, and the result is in the form of a, b, c, d terms. However, the numerical values of a, b, c, d has yet to be obtained. In the following, we're going to show you how to calculate the values of a, b, c, and d. We go back to the partial fractions that represents the fractional function r. The constant a, b, c, and d in these three partial fractions can be performed by equating the sum of partial fractions into the form of an fractional functions, which comprise of the common factor in the denominator of the partial fractions. namely x squared plus 1 and x minus 1 squared, which is the repeated linear factor. The linear factor ax plus b has to be then multiplied with x minus 1 squared. The constant c has to be multiplied with the irreducible quadratic factor and a linear factor of x minus 1. The constant d have to multiply with the irreducible quadratic factor. We expand the numerical functions by opening up the brackets. The expressions in these functions is a simplification from this equation. We proceed by collecting all the coefficients to x power 3, coefficient to x power 2, coefficient to x power 1, and the coefficients independent of x. We can see here ax multiplied with x squared give you a factor of ax cubed. There will be a term cx cubed as well. So the coefficient for x power 3 is a plus c. For the coefficient to x power 2, we have b and minus 2a minus c and plus d. So that makes up the coefficient to x power 2. For the coefficient to x power 1, we have the contribution of a and minus 2b, a c, and there's no contribution from the d term. The coefficient that is independent from x comes from d minus c and b. So we are now in the position to compare the coefficients of x power 3 in the numerator function here to the numerator function in the original r function. There is no x power 3 term in the r function. There is no x squared term in the r function, but there is an x term in the r function and an constant term. Therefore, we can identify the coefficient to x power 3, the coefficient to x power 2 as 0. The coefficient to the x term is minus 2. So we have this. And the coefficient independent of x is minus 4. So we have this equation. Here we have arrived at 4 simultaneous equations with 4 unknown, a, b, c, and d. This simultaneous equation can be solved easily. When you solve these equations, you get the result for a, b, c, and d. After obtaining the values of a, b, c, and d from the previous step, we then slot in the values of a, which is 2, b, which is 1, c, which is minus 2, and d, which is 1, to arrive at the full solutions of the integrations for the rational function r. As a conclusion to this video, we have shown you how to use the method of partial fractions to integrate n rational functions which involve an irreducible quadratic factors in the denominator and a repeated linear factor of x minus 1. The fractional functions is first decomposed into 3 partial fractions. The first partial fraction terms comprise of 1 with the irreducible quadratic factor in the denominator, while the numerators of these partial fractions comprise of a linear factors of ax plus b. The second term comprises of the linear factor x minus 1 with a constant assigned to it in the corresponding numerator, while the third partial fraction term comprises of an denominator with x minus 1 squared and a constant d assigned to its numerator. These partial fractions can then integrated term by term to arrive at the solutions in terms of a, b, c, d. The constants in the partial fractions of a, b, c, d is then solved by comparing the coefficients to the powers of x. That will give you a set of 4 simultaneous equations in terms of a, b, c, d. Solving the set of these 4 simultaneous equations then allows you to obtain the numerical value for the constant a, b, c, d in the expressions of the partial fraction integration.